we present CASPI, Collaborative Photon Processing for Active Single-Photon Imaging. Optical active imaging has several applications. For example, Lidar, fluorescence lifetime imaging, and imaging through scattering media. In active single-photon imaging, a light source illuminates a scene, and a single photon sensor captures the reflected light. A single photon camera can capture individual photons as a function of space and time, providing a 3D photon transient cube. The raw data captured by a single photon camera is quite different from a conventional RGB camera that only captures pixel intensities. A photon transient cube provides a rich source of scene information at extremely high spatial and temporal resolutions. So let's take a closer look at this photon transient cube. Each pixel in this cube provides a histogram of photon counts as a function of time. We can measure various scene properties from these photon histograms. For example, we can estimate the depth at a pixel by locating the peak of the histogram. Then repeating this at each pixel in the cube, we can recover a depth map, as shown here. Under challenging imaging conditions, these photon transient cubes suffer from severe distortions. Here's an example showing strong background lighting. Notice that the depth values are severely distorted. Here's another example with a very weak signal due to a low power light source. Once again, severely distorting the depth map. Our goal is to recover the clean photon transients when operating in such challenging and extreme conditions. We call our algorithm as CASPI, which stands for Collaborative Photon Processing for Active Single-Photon Imaging. CASPI is quite versatile. For example, in a Lidar application, we can use CASPI to recover clean photon histograms and reliable depth maps even under extreme lighting conditions. In fluorescence lifetime microscopy, CASPI can enable reliable lifetime estimation with ultra-low photon counts. Without CASPI, single photon cameras can perform well in the high signal and low background regimes. With CASPI, single photon cameras can now operate with orders of magnitude lower signal and higher background illumination. This considerably expands the scope and operating regimes of active single photon imaging techniques. Let's look at a Lidar application. Here's an example scene and its ground truth depth. With a strong enough laser and negligible background light, we can get reliable depth estimates with simple conventional approaches such as matched filtering. But if there are too many background photons or too few signal photons, this method fails to recover depths. CASPI enables reliable, high-quality depth estimates even in these challenging photon flux regimes. Imagine a single photon LiDAR on a self-driving car. It must recover 3D object details at long distances even under bright sunlight. But this is an extremely challenging task due to the low number of signal photons and strong background light. CASPI enables depth recovery of distant objects even in these extreme illumination conditions where state-of-the-art approaches often fail. Observe the depth details captured on the building, which is almost 100 meters away. Next, we show results on real-world data captured from a single photon LiDAR hardware prototype. We show two operating regimes: extremely high background light with 20,000 lux for the deer scene, and extremely low signal photon regime for the face vase. In these difficult conditions, it is almost impossible to recover 3D geometry with traditional approaches. But CASPI recovers accurate geometry under these extreme scenarios as well. We now show results of CASPI with fluorescence lifetime imaging microscopy, or FLEM. Here is a fluorescence lifetime image obtained with roughly 10 photons per pixel and processed with gold standard maximum likelihood estimation and state-of-the-art BM3D denoising. Here's a lifetime image obtained using Caspy. Even with as few as 10 photons per pixel, Caspy enables reliable lifetime estimates much closer to the ground truth than state-of-the-art approaches. Now, segmenting the cell nucleus is an important downstream task performed on film images. This can be quite challenging if the lifetime image is noisy to start with. With Caspy, the cell nucleus and the background segmentation is nearly the same as the ground truth. Here, we show a time-lapse sequence of live cell autofluorescence film. Autofluorescence is a useful non-invasive diagnostic indicator, but it requires using extremely low laser power to avoid damaging the cells being imaged. Even in this low signal photon scenario, Caspy enables reliable lifetime estimates for video rate live cell film imaging. Here's another time-lapse sequence of autofluorescence film. Caspy again provides higher quality lifetime images than a widely used commercial software package. In summary, Caspy is an application-agnostic, tuning-free, and training-free photon processing technique that enables reliable scene property estimation in extreme lighting conditions for a wide range of active single-photon imaging applications. We envision Caspy to become a basic building block of general-purpose photon processing units in future single-photon cameras.